Bé, doncs comencem el seminari. Veient les cares, crec que puc presentar l'Estefania en català. Doncs també és un plaer presentar la Stefania Sandoval. L'Estefania ha fet contribucions molt importants al grup i és una experta en sistemes de baixa dimensionalitat, relacionat amb materials de carboni inorgànics principalment. Es va formar amb la professora Amparo Fuertes i a mi mateix, fent la tesi doctoral. Ha estat en centres de reconeixement internacional com el del professor Rao a l'Índia, l'Stellacci a Suïssa, i llavors va fer un postdoc de 2 anys amb el Martin Kalbach, que és un expert en espectroscopia i materials de carboni inorgànics també. I a part del recorregut científic, jo crec que cal destacar que l'Estefania ha dedicat també molt temps i moltes hores a implementar un laboratori per biomedicina, on es va encarregar de tots els pliegos abans que hi hagués, abans que tinguéssim suport a l'ICMAB, i això és una feinada impressionant. Va també tot el tema d'un cop implementat aquest laboratori i de l'equipament i decidir on aniria cada endoll, també va tenir el valor d'implementar l'ISO de qualitat, que hi ha grups que tenen una persona només que es dedica a aquest tema, i és l'encarregada del sistema d'ISO de 9001 que tenim implementat des de l'any passat, i va fer el seguiment, que és una tasca brutalment impressionant. I res, llavors, això, les experteses són sistemes de baixa dimensionalitat i havíem parlat de síntesi i modificació de superfície i com podem tunejar les propietats dels materials a través de dopatge, d'emplenar isòtops de carboni i d'aquest tipus de sistemes. Doncs, cuando quieres, Stefania.
¿Me escuchan? ¿Sí? Vale, muy bien. Okay, thank you, Gerard, for the introduction. So the idea of this talk is give like a general overview of the possibilities that we have to modify the structure and the properties of low-dimensional materials by surface modification and doping. So okay. This is not working. ¿No? ¿Perdón? Okay. No? Yes, now. Okay. Nice. Okay. So I have divided the presentation in a first introduction about carbon-based and inorganic layer materials and 2 different approaches: the synthesis and modification of two-dimensional layer materials, which include functionalization and doping, and decoration with metal oxide nanoparticles. The third part is dedicated to the endohedral functionalization of carbon nanomaterials, which also include template-assisted synthesis of one-dimensional van der Waals heterostructures and the controlled release of encapsulated crystals, and a brief summary of the talk. So, as we know, carbon-based layer materials, I mean, there has been a revolution with the discovery of graphene. So more or less the most relevant moments in history of carbon-based layer materials start in 1957 with the synthesis of new graphene oxides systems, then the discovery of nanodiamonds and fullerenes, and then the development of different one-dimensional systems and zero-dimensional systems that include multi-wall carbon nanotubes, single-wall carbon nanotubes, nanohorns, and finally with the isolation of graphene and the measurements of their properties in 2004. So afterwards, myriad of applications have been reported on these systems, and the properties of them have been improved by doping functionalization. From here, then, a wide number of two-dimensional materials and layer materials have been also reported with a wide number of application and properties. So in principle, carbon-based layer nanomaterials can be divided in function of their structure, morphology, and dimensionality. And the classification can be done in terms of the bond hybridization pattern. So there is the first one correspond to the ones that has sp2 hybridization. These include one-dimensional systems, zero-dimensional system, and also there are sp3 hybridization systems, which are basically a derivative of diamonds. So there are other systems which combine both hybridizations, and therefore they have also combined properties. So the sp2 hybridization of graphene and their derivative is responsible of the hardiness, Young modulus, and high thermal conductivity and electronic properties of these materials, which is very relevant for applications. And also, there have been many efforts in changing the properties of this material to improve solubility, reactivity, and also to enhance the optical and electronic properties of them. As I mentioned, ideally, from graphene, we can prepare other derivatives which can be built by wrapping, stacking, or rolling. And then we can obtain materials with enhanced properties like nanotubes, fullerenes, or onions, or carbon nanohorns. The way in which this graphene layers is wrapped also define the property of the material. So we can obtain chirality-dependent systems, as in case of single-wall nanotubes that can be metallics or can be also semiconducting. So in terms of the synthetic methods, there have been many proposals. The one which is like a more relevant and generalized is the exfoliation. However, the problem with this technique is that the exfoliation of two-dimensional materials is not an scalable process, so it has these limitations. However, there have been developed other approaches where graphene precursors can be exfoliated and oxidized by different methods to obtain, that should be obtained by chemical oxidation of graphite, and then afterwards we can also obtain reduced graphene oxide by different techniques of reduction. Also, the properties of graphene can be changed, but can be tuned by this oxidation, and we can also obtain materials with high hydrophilicity and chemical reactivity, which allows also the further modification of the material. So there have been many precursors. The protocols are usually oriented towards the obtaining of scalable and also environmentally friendly protocols. And so I was describing top-down techniques. So there are other bottom-up techniques also for the synthesis of the materials. In this case, CVD is very widely used technique that usually use different carbon sources in presence of a catalyst, and is a treatment at high temperatures. Also, there are other approaches like conversion inside carbon nanotubes. Here, for example, we can introduce other carbon allotropes like fullerenes, and we can prepare from single-wall carbon nanotubes, double-wall carbon nanotubes. So there are many approaches we can use. As I mentioned, usually the precursor should be environmentally friendly, and also the preparation of other carbon nanostructure can be obtained by these techniques. As I mentioned before, after the preparation and the study of this two-dimensional carbon-based nanomaterial, there have been like a revolution. So we have now reports of different inorganic nanotubes, two-dimensional materials, which usually come from van der Waals solids, and these materials present different properties, mainly induced by the electronic characteristic of the structure of the material. These materials also are prepared by different approaches, but exfoliation is the most widely used. Which are the main challenges of this these techniques. These techniques, in order to obtain materials which are useful and are useful for applications, we need materials with low defects, we need materials which are clean, and we need protocols which are they don't produce side products. So this is a very big challenge. The main drawbacks of the processing is that these materials have a low dispersibility, and also restacking and agglomeration usually occurs because they tend to reestablish the van der Waals structures of the multi-layer systems. That's why conventional processing techniques should be changed, and modification is an alternative that provides the possibility to work in a scalable manner with these materials. So which is desired? We need scalable and efficient routes, we need selectivity toward the formation of the structure without side products, and also we need systems which are stable, because one of the main problems with the inorganic layer system is that usually they are air sensitive, so they degrade over time with air and exposure to the environment. So among the synthesis, among the modification strategies to improve the properties, we have like different defect creation. So the first one is the creation of point defects. It include vacancies and dislocations, grain boundaries, and chemical functionalization, which is one of the most widely reported. In case of chemical functionalization, we can prepare materials which are modified non-covalently with organic molecules, or also with other inorganic systems. We can make covalent changes in the basal plane, and also we can induce decoration with inorganic system. We can be oxides or metal by themselves. We can make in situ and ex situ modifications. So then one of the more relevant and recently applied approach is the scrolling, the creation of defects by inducing curvature of the two-dimensional system. So this way we can also prepare nanotubes, as I mentioned. We can rip, we can fold, and create defect by inducing deformation wrinkles. And therefore, afterwards, this one-dimensional system that I created by folding can be also modified. So we can decorate, we can also make endohedral synthesis, encapsulation of different materials, which can be or other carbon allotropes or inorganic and organic system. So carbon nanotubes can, and in general, other inorganic nanotubes can work like nanoreactors for introducing different systems inside the surface. Finally, which is also relevant and is nowadays being reported, is the formation of van der Waals heterostructures. These van der Waals heterostructures combine the properties of different inorganic systems, so we can tune the property of the material by the interaction of layers. We have different composition. And finally, this heterostructure can be also formed by inside one-dimensional systems. So doping, which is also relevant, include the modification of the band gap of the structure by including dopant agents, which can be like metals or non-metal atoms, in the structure of the systems. Okay, as I mentioned, main challenge are obtaining samples with differentiated properties. So there is a lack in the presence of scalable and selective processes and the low yield of this process. There is no rigorous control of growth environment. So the problem here is that we cannot control the crystallinity of the system we are creating due to we don't know how they are forming. And also in some approaches, purification and separation are needed. There are some approaches that include ultracentrifugation that sometimes are reported that can separate nanotubes with different properties or filling degree, but this is not very developed. And finally, in case of the exfoliation, there are difficulties in the transfers to suitable substrates, and also contamination and defects are an issue. Okay, so then I will show some approaches which we are developing about in order to improve the properties of two-dimensional layer systems. So the first one consists in the doping of graphene using the ammonolysis technique. In this case, what we have done is introducing nitrogen, taking advantage of the presence of oxygen groups in graphene oxide. So this graphene oxide has been prepared by the Humer's method. Then we use pure ammonia gas. And using this technique, we were able to obtain materials with very high nitrogen content. So we determined the presence of nitrogen by XPS. And depending on the temperature we use, we were able to obtain, in some cases, mixtures of aliphatic groups, and in other cases, only doping. So we are able to include amide groups, pyridinic, pyrrolic, and also graphitic nitrogen within the structure of the material. As mentioned, we can tune both natural content of nitrogen-based group, and then afterwards, we also perform high temperature treatment. So this nitrogen dope system, we treated under inner gas, and then we were able to modulate, to tune the characteristic of nitrogen inside the structure. So we also create a new group, pyridinic N-oxide, which, as we will see later, also provide new properties to the material we have synthesized. Depending on the nitrogen and the nature of the nitrogen that we introduce inside the system, we also change the hydrophilic character of these materials. Taking graphite as reference, materials with the presence of covalent groups attached to the surface, let's say amines and amide groups, show a larger hydrophilic character compared with nitrogen atoms which are introduced in the conjugated system of graphene. And also, we improve the dispersibility in water as the material that we prepare using this ammonolysis approach. But there was an issue. We were not able to obtain differentiated samples. So that's why we developed a room temperature ammonolysis process which only introduce aliphatic groups. This is important in terms of the dispersibility and application of the material, because materials which are not, which don't have functional groups attached, covalent groups attached to the system, they are not dispersible in solvents, in aqueous solvents. So using this approach, which was only 5-minute treatment, we were able to introduce only amines and amide groups in the system, obtaining up to 5.2% of nitrogen in the structure. Of course, we study the effects of flow of nitrogen, time, and temperature, and the presence of these nitrogen groups were confirmed by XPS. Okay, so then in some cases, the presence of aliphatic groups is required, but the presence of defects which are provided by the covalent groups also decrease the conductivity and the properties of the material. So the opposite trend should be also desired. So this laser-assisted technique was developed in collaboration with Ángel Pérez. And in this case, we use a laser-assisted technique to synthesize systems strictly doped. So in this case, we use different lasers with different fluence and also obtain up to 5% of nitrogen into the structure, but in this case, the formation of pyrolytic fraction was favored. So this way, we are able to tune the properties of the materials by selecting the group we are introducing into the structure. These both approaches are simple, fast, low cost, and efficient. About the properties we provide to the materials. So this work was published in 2014, and here we highlight the ability of nitrogen to provide thermal stability to the system. Already in the sample where we introduce only aliphatic species, we see an increased thermal stability of the material. So the first fall corresponds to the presence of aliphatic groups, but in this case, the fall corresponds to the combustion of the skeleton of the material. So by introduction of nitrogen into the system, we are able to increase the thermal stability of these monolayers. So in case of doping, there was an accurate increase. So by doping, we made like thermodynamic calculations, and we confirmed that by doping we were able to increase up to 14% the stability of the system against combustion in air. So these materials are like potential, can have potential applications as flame retardants. And as I mentioned before, this sample, this TGA corresponds to the sample treated at high temperature. So the modification under argon and on the inner atmosphere. So the inclusion in the system of this pyridinic oxide system also increase the property of the material. So this TGA corresponds to samples which were treated at 220 degrees, which initially had 14.7% of nitrogen. So we obtain samples which doesn't have functional groups, covalent functional group, aliphatic groups, but we are creating oxidized system that can enhance the properties of the materials. One important thing about the determination of the thermal properties of these materials is making like a proper characterization. So usually thermogrametric analysis is used for this characterization, but what we observe is that sometimes there is no like a concrete line in the conditions we use for determining this thermal stability. So we started to study how the parameters employed for TGA can have an influence in the results we obtain, because finally this is like an orientation of the properties of the materials we obtain. So in this study, what we did is like evaluating the thermal analysis of reference samples. In this case, these are reference of carbon nanotubes, and we change flow rate, mass employed for the characterization, and also heating rate. In the case of flow and the mass of the system, we didn't observe important variations. Of course, this mass also is related to the volume of the sample. So if we have samples with low density, we will need like more sample inside the crucible, and then we will need to be careful about the amount of sample we put. But in case of temperature, the heating rate employed for the characterization, there was a very big deal when increasing the rate used for TGA. So this could be because, of course, there are internal processes which are also exothermic during the system. So we need to be very careful when determining the conditions we will use for characterizing these materials. This was also extrapolated to the determination of the thermal stability of end-up graphene oxides in order to see if this is reproducible. So we observe similarities in the measurements and the effects of the heating rate in the measurements using TGA. So then, after taking like a careful characterization of these materials, we also observed and we apply the properties we had in the building of new three-dimensional system. So in collaboration with Professor Concepcion Domingo, we prepare aerogels, graphene oxide aerogels, and we also dope using hydrazine and also ammonolysis. And in this case, we obtain systems which were very, very stable in presence of flame. So this is an approach in the case that we can scale the material we are working and preparing three-dimensional system based on layered materials. These materials also presented very high mechanical properties. They are very stable and have different behavior when they are in presence of they are dry or in presence of some solvents. Okay, continuing with the developing of new characterization techniques and also obtaining proper characterization of this system, we observed that XPS, even though it's a very useful technique, XPS has a problem, and is that the area where the binding energies of the aliphatic groups appears overlaps with the signals of pyridinic and pyrrolic systems. So we use a modified Kaiser test, develop this system using an abduct to determine the presence of primary amines in the system. So this approach, this characterization, enabled to discern between the aliphatic groups present in the material and pyridinic or pyrrolic. This technique also was also confirmed by TGA-MS, which is also useful. In case of TGA-MS, we can correlate the temperature of the fall, of the oxidation of the material, the release of the aliphatic group, with the mass of the mass spectra. So we differentiate like characteristic peaks corresponding to aliphatic groups like pyridine and amide and amide. So we can also have an idea or establish a relationship between the temperature of combustion of the system and the group which is released. Okay, so another approach that we can use for modifying the properties of the material is making non-covalent doping, in this case, by the decoration of graphene oxide or graphene derivatives with inorganic oxides. So in this work, we make the modification by using iron derivative and iron salt that was reduced under microwave techniques. And we were able to obtain graphene oxide decorated with spion nanoparticles. These samples find applications in MRI. And one thing that we here consider is that this protocol, which is an in situ protocol based on the decomposition of a salt, usually doesn't allow the control of the loading of the nanoparticles onto the graphene oxide. So we tune this loading by changing the organic group attached to the precursor. So by using olates and acetates, we were able to change this loading and tune the separation of the particles, which usually agglomerates onto the graphene oxide layer, but also tune the amount of particles which are attached on top of the material. But then even though we are able to change the loading, we have the same problem, and is that the distribution of the size of these nanoparticles onto graphene oxide is not homogeneous. So we don't have, in general, narrow distributions. So the protocol is fast, it's simple, it's useful, but we have poor control of size. So taking this into account, I have developed a solvothermal synthesis of these nanoparticles. By two steps approach, this is an ex situ approach. I prepare oleate functionalized cobalt ferrite nanoparticle, which are very stable, are very crystalline, and they have a very narrow size distribution. Another advantage of this approach of having a two-step protocol is that we can tune the properties of these nanoparticles before attaching them onto the surface of graphene oxide. So we can even prepare mixed magnetic nanoparticles. In this case, for example, I have done a two-step protocol in which I prepare 6 nanometers nanoparticles in all cases, and then prepare a core shell which can be formed by the same crystal, I mean the same cobalt ferrite, but also we can change the counter ion, and we can prepare mixtures of different magnetic materials. So in this case, for example, we have a manganese nanoparticle covered by a shell of cobalt ferrite nanoparticles. So we can tune the magnetic properties of the particles before attaching them onto the graphene oxide. So then, of course, I did the second step, which is also solvothermal, and this protocol enabled the tuning, size, and composition. We can prepare, as I mentioned, nanoparticles with different properties. We have narrow size distribution, and we can also select the stabilizing agent. And this is also important because before attaching these particles onto the graphene oxide, we can interchange the stabilizing agent. And this provides the possibility of having particles which are dispersible in different solvents for different applications. As I mentioned, we made high-resolution TEM for the characterization. These particles are stable, have a very narrow distribution, and we also can tune the loading of the particle onto the graphene oxide by changing the amount of precursor we put into the reactor. This is, for example, the particles prepared using the same protocol, but using the in situ approach. I mean, putting the precursors inside the reactor, but not preparing the particles before. So this is, we can see that in this case, for example, we have very big particles, and we cannot change we cannot tune and control the size of the particle. And also the protocol is very versatile because it can be applied to the modification of other nanostructures. One advantage of this technique is also that the presence of nanoparticles in the reactor also induces the reduction of graphene oxide. That is usually one of the main issues of preparing samples with graphene oxide, because when you have samples which are not completely reduced, the electronic properties of the material change, and this can affect the application. So in this case, the presence of these metal oxides in the system also induces a very high reduction of the graphene oxide. So we can say that we have a properly reduced sample, and we only have particles attached and not other aliphatic groups. This is, for example, a comparison between the sample prepared by these methods, and this one is the sample prepared with oleate by microwave, and here we can see that we still have some aliphatic groups attached to the system. This material was proof for the cyclohexane oxidative dehydrogenation. This is a reaction which is very important in terms of the production of cyclohexane. And we can see that the material prepared loaded with the small particles, which correspond to the left side, have like a better behavior compared with best conversion compared to the samples prepared with the large nanoparticles. Okay, and now I will continue with the endohedral functionalization of carbon nanomaterials. So this is an approach which involves the concept of inducing defects and changing the property of the material by scrolling or by wrinkling or any other curvature onto the 2D material. So we have used here in this approach carbon nanotubes as templates for the production of inorganic van der Waals solids, one-dimensional inorganic van der Waals solids. The advantage of carbon nanomaterials in particular of carbon nanotubes, they have a wide variety of diameters. They are platforms which are robust. The growth can occur only in one direction. And due to the diameters, they can encapsulate different nanocrystals, a wide variety of nanocrystals. We can then use single wall and multi-wall carbon nanotubes that can also provide specific properties to the systems. So one issue is that in general, we need a previous purification of the materials because they usually contain remnant catalyst from the synthesis, which can affect the properties. So the advantage between the endohedral versus exohedral functionalization is that it allows isolating sensitive materials, which usually are damaged by contact with air. Carbon nanotubes can act as potential nanoreactors, and also confinement effects can also improve the properties. So we have two different confinement effects: the confinement of electrons along the direction of nanotubes, but also the confinement of the crystal inside the surface of carbon nanotubes. So usually this endohedral functionalization is done by ex situ and in situ filling. There are some reports, but in this case, filling yields are very low, in which the author tried to encapsulate inorganic system, hollow inorganic system inside carbon nanotubes. So in this case, this is a report of the CVD synthesis where we introduce methyl chalcogenide inside the nanotube that they only reach 1% yield. So then our approach is trying to take advantage of these properties to obtain hollow system heterostructures. One thing that is very important is that we need to select crystals which have surface tensions. And we need to consider aspects as by viscosity, crystal nanotube energies, and vapor pressures of the inorganic nanomaterials. So the first approach is the molten phase capillary wetting. In our group in 2014, it was reported for the first time the synthesis of lead iodide encapsulated inside carbon nanotubes using this molten phase approach. So then what we did is try to extrapolate this synthesis to a variety of inorganic halides. So we were able to use different solid van der Waals solids that include zinc iodide, zinc chloride, cerium compounds, terbium compounds, gadolinium chloride to prepare these heterostructures. So this systems were characterized using high-resolution microscopic techniques. And we also studied the possibility of tune the ratio between the tubular structure, which usually is very low. So because usually the formation of solid crystals inside carbon nanotubes is favored. So in this case, we use different temperatures, different conditions in order to improve the possibility, reaching up to 60% of nanotubes against other structures by increasing the temperature of treatment. But of course, there were still other nanostructures present inside the nanotubes. So yes, confinement. Another advantage of this technique is that we were able to change the structure of the material by confining. This is an example of samarium chloride, which a structure in bulk is not layered, and when we confine this system inside the nanotubes, we were able to prepare a nanotube. So this is like a not very widely explored approach to change the crystallinity and the structure of the material by confinement. So following with the tuning of the ratio of the structure which are confined inside the material, so we also developed a new technique in collaboration with Angel Perez, in which we use laser to selectively prepare hollow heterostructures inside carbon nanotubes. With this technique, which was ultra fast, we were able to obtain up to 90% of tubes against the other approaches where we obtain mixtures between rods or nanowires and nanotubes. So this is a very efficient protocol to selectively prepare hollow heterostructures. And also, we also observed in these materials that the material exhibit the properties of both the guest and the host properties. And one advantage of using carbon nanotubes in these systems when we want to apply this material for electronics, for instance, is that carbon nanotubes are transparent. So in this case, up to almost 80% of the light reached the inorganic nanotubes, and we were able to use this material as transparent hosts, let's say. So another problem or another issue is that there was like a threshold in the formation of nanotubes inside carbon nanotubes or inside tubular nanostructure. There was reported that up to or only below 10 or 12 nanometers, single layer carbon nanostructures are synthesized. And this is a problem because usually when you increase the number of layers, you also change the property of the material. So the synthesis of single layer systems is desired. That's why we evaluate the formation of this nanostructure inside carbon nanotubes. Because before, wider structures, like for example, tungsten sulfide were used, but in this case, or rod or multi-layer inorganic systems were formed. So we use pyrolytically stripped pyrograph carbon nanofibers to prepare this system, this hollow system. So using the molten phase approach, in this case, of course, carbon nanoplatforms were able to encapsulate both rods, but also carbon nanotubes, which reach up to 60 nanometers diameter. So this is the first time that single layer nanotubes is encapsulated in a big platform. Okay. However, only 2% of these slings correspond of this nanostructure corresponded to slings. So we switched to another approach. So we employed a sublimation approach in order to increase this ratio, to increase the amount of nanotubes inorganic nanotubes that are created inside the fibers. So in this case, we also were able, with the sublimation approach, taking advantage of the formation of the gas in the reactor, in the silica ampoule, to prepare these nanostructures. One advantage of the sublimation approach is that the protocol is clean, because when we mix in the molten phase approach, we mix the materials together. So usually the removal of external material is required. In this case, these samples were practically clean under the characterization we performed. And we also confirmed that we have nanotubes, inorganic nanotubes, inside the fibers. Compared to the molten phase approach, we drastically increase the ratio between the nanotubes and nanorods, and confirm that fast treatment, I mean, in only 5 minutes, we can increase until 10 times the amount of nanotubes we can encapsulate inside the fibers. And also, we also were able to tune the length of the rods which were encapsulated inside. Apparently, there was no a trend between the time of treatment and the formation of nanorod, but at 72 hours, almost none short nanorods were observed. So this suggests that during the treatment, we sometimes sinterize the crystal which are inside the material. So as I mentioned before, one of the main issues of the synthesis of this material is that we cannot control the growth, because we don't know the mechanisms of growth of this material inside. So we take advantage of some observations in TGM, as for example, the formation of a slit under the E-beam. We observed that single-layer nanotubes were formed. So we evaluate the effect of the electron beam on the formation of new nanostructures. In this case, we saw that we have junctions, namely one nanorod aside to a nanotubes. We see that under the E-beam, under different energies, the rod practically dissolve or evaporates. And we can observe that the creation of single layer, multi-layers, bilayers, and also triple layers of the nanotubes inside. So the electron beam has an effect on the formation of these nanostructures. This is a video, and we can see, sorry. So here we can see how the system evolves along time. One thing is that this way we can control the time in which this process occurs. And also this process is dependent on the temperature of the system. When we perform treatments at low temperature, these changes occur at a lower rate. Another observation we obtained with this experiment is that, as we know, STM and these microscopic techniques are based on the C contrast. So with these experiments, using these experiments, we observe that even though in some cases, in some specimens, we don't see apparent changes in the density of the crystal, we can see the appearance of a cloud during a white cloud during the characterization of the material. So this occurs simultaneously to the appearance of lines, which suggests that the homogeneous formation of the nanotubes inside the carbon nanotube. So these are preliminary studies which we performed in order to evaluate the growth of these nanotubes inside these big fibers. Okay, we also employed, these this approach, the sublimation, to encapsulate a variety of systems. So this work have been developed by Alejandro Cuesta. Here he used multi-wall carbon nanotubes to encapsulate different crystals with different properties, with interest, for example, with magnetic properties or interest in thermoelectrics. So, and also he developed, he make like correlation between the electronegativity of the container of the metal and the formation of nanotubes. Apparently, there is no correlation between the formation of nanotubes, but it is there is an important trend, an increase in filling when the difference of electronegativity of the material is high. So these are like preliminary studies which are we are planning to perform also along with theoretical also characterization in order to understand how these materials grow. As I mentioned, he has filled in other systems which have been characterized during his stay at EMAD in Belgium, and he has been able to characterize the crystallinity of the system, and these materials have been also encapsulated inside single layer nanotubes. These are also iron iodides. As I said, the approach is versatile, and we were able to detect the presence of the nanotubes inside. Importantly, is the encapsulation of bismuth tellurides. In this case, we prepare this material by using a transport agent, iodine, in order to facilitate the migration of bismuth telluride inside the tube and the sublimation, and also depositing inside the tubes. This material was also characterized inside the carbon nanotubes, and in this case we didn't obtain tubular nanostructure layer bars, which structure match with the structure of the material in bulk. And then he encapsulated the material in single wall carbon nanotubes. One issue in the encapsulation of these systems, in the formation of this system, is that it's very difficult to separate filled nanotubes from empty nanotubes, which is like a drawback in terms of the application of the material. So he also developed a separation approach via density gradient ultracentrifugation. In this case, he used different densities, solvents, solution with different densities to separate the material by ultracentrifugation. The sample was characterized by Raman, and he observed that after the treatment, he was able to separate the bundles, which are located at the bottom of the tube, from the gray area, C, which is the area with the filled carbon nanotubes, and from the empty one, which deposit on top of the system. The characterization also allowed the differentiation, because he observed a shift between the signal of empty tubes, this one, the pink one, against the red one, which undergo a shift in the Raman. So this characterization technique can be also used for the characterization of for discerning the presence of tubes, empty or filled tubes inside carbon nanotubes. So finally, this was a study we developed in order to evaluate whether we were able to release the material from the carbon nanotubes. This is important in case of applications, for example, in biomedical applications, for releasing the material inside, and carbon nanotubes can be used as transporters from the material encapsulated. So taking advantage of the taking advantage of the affinity of fullerenes as with some solvents, we were able to here's better. Okay, so we were able to to release or maintain the material inside. So in this case, for example, for the release approach, we encapsulate lead iodide, which is used like reference because the contrast, not because the utility of the material in biomedical applications, but because it's very easy to see on their TM. So what we did is fill nanotubes with lead iodide, then cork it with fullerenes on their gas approach, and there we use ethanol as release agent. So in case of this approach, we were able to remove almost all the material from the sample. However, when we encapsulate this material and afterwards use water as solvent, the lead iodide remain inside the nanotube. So this strategy can be used for corking or release of the material inside. So we can take advantage of these approaches in order to selectively modulate the material contained inside the nanotubes. So this is more or less an overview of the evolution of these techniques we have developed. So then we are able to modify the structure and properties, physicochemical properties of the two-dimensional materials by doping and also by decoration. These materials have applications like catalysts, and also as they have very high stability against oxidation, but also we are able to prepare different heterostructures with different properties using nanotubes as templates. Nowadays, what our perspective in terms of the characterization of developing these approaches is the in situ characterization of the material and also the formation of different systems by developing different selective approaches. This can be done by taking advantage of spectroscopic techniques, but also microscopy, which provides many tools and integrated tools for the characterization of these systems. And that's all. Okay, so these are some preliminary results of the induction of strain by mixing, by exfoliating two-dimensional material onto different nanostructure. Of course, we can take advantage. This is some studies I have developed during my postdoctoral stay in Prague, and where we are also inducing the strain of two-dimensional materials by using different particles, namely magnetic nanoparticles or nanodiamonds, which can provide different properties to these systems. This is, for example, one work of CERS, which is the enhanced spectroscopy using metallic particles. Here we have seen that this material, MOS2, which has potential application as of optoelectronic material, can be their properties can be tuned. The photoluminescence can be tuned by depositing this silver onto their surface. So we obtain shift in the optoelectronic properties, but also we can have switching of the Raman spectroscopy, which suggests that we are changing the electronic properties of the material. And that's all. This to acknowledge all the people have been working a long time, and I'm open to questions.
Thank you for this nice overview of all the work you have done. So if there are any questions in the room.
Thank you very much. I have a question related to the lead iodide. When you say the structure of the material changes, you mean the crystallographic structure?
Lead iodide? I think
I mean, you were showing TEM images, but did you look at the crystallographic structure?
in principle, it's the same. I mean, in which in fibers or?
No, I am wondering if you observe
I thought that you were
stabilization of
this.
a different polymorph or polytype inside the tube, different from.
So we haven't seen the structure of lead iodide has changed. Let's say when we analyze the crystal structure similarly to the polymorph, the layer, the most common layer structure. What we have seen, that is something that is under study because we don't have many data about it, but is that, for example, in this case of samarium chloride, the crystalline structure should be orthorhombic. And this is in bulk should be like three-dimensional system. But when we encapsulate it inside, we see that it's layers. So this was a quick observation in a study we did for other application, where we observed that we have like layer structures. So in principle, there are many studies in which when you encapsulate the systems, different systems, potassium iodide, other crystalline structures that you can tune the properties when encapsulating depending on the diameter of the nanotubes. Of course, you know that the crystals somehow try to accommodate inside. So this has happened, but with lead iodide, we didn't observe that.
Thanks.
Thanks very much for the talk, Stefania. I had a couple of questions. The first one is very simple, I guess, for you. When you do the ammonolysis, how do you do that? I mean, what is the experimental setup?
So we have a powder. We put like a sandwich furnace. We put the material in a crucible, in a boat, silica boat, alumina boat. Put it in the center of the furnace, and then we introduce a flow of pure ammonia inside the furnace. We can tune the flow of ammonia, and this way, in principle, you can tune also the temperature. So by increasing temperature, you can modulate the amount of nitrogen that you introduce inside. So it's very simple solid gas reaction inside the tubes. It's powdered in contact with gas.
Yeah, I thought that was interesting. I mean, in the sense that it's a very inefficient process, I suppose, because you have a relatively low pressure of gas over the inorganic substrate. So are there other approaches to do that, like using things like urea or inorganic nitrogen sources?
Yes, there are many approaches to dope graphene oxide. However, what I have seen is that they are very dirty because usually they are like high temperature decomposition of nitrogen precursors. You can create many defects when you use these precursors. Also reduction of the system, and you cannot tune the amount of nitrogen that you introduce inside. And also, yes, it depends on the amount of ammonia you put, because we have seen that in only 5 minutes in contact with ammonia, we can reach very high values of nitrogen inside. So the protocol is efficient because you don't need like a long time of exposure to pure ammonia to obtain like high levels of doping. This mostly depends of the amount of functional groups you have at the beginning. So if you have graphene oxide, we have like between 25–40% of oxygen, you have high doping level. So it depends on the precursor you use. But in my opinion, it's more efficient than other doping techniques.
Okay, fine, thanks. I also had a question related to what Maddi asked you about the lead iodide. So what's the redox chemistry of lead iodide? I mean, because when you're thinking about an inorganic material like that in contact with an organic material, in an electron beam. I mean, there's a lot of redox processes that could go on, I suppose. Do you have any observations that might suggest that there's something going on chemically there?
No, so we haven't evaluated the redox properties of lead iodide. In fact, what we are doing now is evaluating redox of other systems like iron iodide and nickel iodide. But in terms in case of lead iodide, we didn't evaluate it.
Okay, thanks.
Hi, Stefania. Have you tried to fill the carbon nanotubes with metal oxides? Is it possible?
Yes, usually for filling with metal oxides, the techniques that are usually used are in situ techniques for metal oxides. So you can also use a precursor, another precursor, and then oxidize it. This is also possible. But in general, filling carbon nanotubes with oxides is done by CVD or R discharge or other in situ approaches. That before was like an accident. No? At the beginning was like they were trying to prepare nanotubes. Then with the catalyst they introduced inside, it was somehow an accident. But there are approaches that can oxidize or reduce the material you can put. So you can use like a precursor, like organic precursor, or a salt to do it. But the problem if you use like a metal and you want to decompose it is that you don't fill but decorate with nanoparticles. So usually the decoration of the surface, the external surface is preferred against the filling. So there should be a two-step process, but we haven't filled with oxide.
Maybe a good idea will be to fill the nanotubes with precursors, metal organic precursors, and make them react inside with annealing or high temperature annealing or whatever, and maybe you can get different structures, no? Because it's confined.
The only problem is that if you oxidize in air, you can burn the nanotubes. So you should use another protocol to oxidize it because, of course, they are very stable, but I don't know, above 600 degrees, you burn it. So it's not like straightforward. But yes, it could be done.
Okay, thank you.
Okay, good, thanks. So I think that we will stop here because it's getting late. So let's thank Stephanie again for the talk.
Okay.